Ladies and gentlemen, today, we delve into one of the most controversial and enduring debates in the history of science and philosophy, the hypothesis that the Earth is flat. While it may sound absurd to many in modern times, history reveals that this idea once dominated human understanding for thousands of years. From ancient Babylon to Egypt, and even among some early Greek philosophers, the concept of a flat Earth shaped the worldview of entire civilizations. But why? And how has this notion persisted, despite overwhelming evidence supporting the Earth's spherical shape? To truly understand, we must examine the origins, the evidence, and the arguments that surround the flat Earth hypothesis. Reliance on observation and its limitations. In ancient times, human understanding of the natural world was confined to what could be directly observed. This reliance on empirical observation laid the foundation for the flat Earth hypothesis. Visual perception of flatness. From a ground-level perspective, the Earth appears flat because the curvature is imperceptible to the naked eye over short distances. This led to the intuitive assumption that the Earth itself is flat. Phenomena like the horizon extending in a straight line further reinforced this perception. Without instruments to measure vast distances or curvature, early humans lacked the means to challenge this conclusion. Absence of advanced technology. The inability to travel long distances, either by land or sea, limited the scope of exploration and the chance to observe phenomena, e.g., ships disappearing hull first over the horizon, that might suggest a spherical Earth. Tools like telescopes or mathematical modeling, which are crucial for modern astronomy, did not exist, keeping these early societies reliant on rudimentary observational data. Ancient cosmologies and their influence. Cosmological beliefs from ancient civilizations were deeply intertwined with mythology and religion, shaping their worldview and understanding of the Earth's structure. Mesopotamian and Egyptian models. Mesopotamian cosmology depicted the Earth as a flat disk, often surrounded by a primordial ocean. The heavens were seen as a dome covering this disk, supported by mountains or pillars. This conceptualization blended physical observations with religious narratives, making the flat Earth a central aspect of their cosmological systems. Egyptian cosmology similarly viewed the Earth as flat but added their unique mythological elements, such as the goddess Nut arching over the flat Earth as the sky, while Geb represented the ground. These cosmologies illustrate how early societies explained their environment through narratives that were accessible and aligned with their spiritual beliefs. Religious reinforcement. The flat Earth hypothesis was often supported by religious doctrines, which provided explanations for the universe that aligned with observable reality at the time. The role of religion in reinforcing these ideas cannot be understated, as religious institutions were among the primary sources of knowledge and authority. Philosophical contributions and evolution of ideas. Greek philosophers such as Anaximander and Thales represent a critical transition from mythological to proto-scientific reasoning. Anaximander's cylinder model. Anaximander's vision of the Earth as a cylinder is particularly noteworthy. It reflects an attempt to move beyond simplistic flat disk models, suggesting an early curiosity about the three-dimensional nature of celestial objects. The idea of the Earth being suspended in space was revolutionary, indicating a shift from a purely mythological worldview to one that entertained abstract, naturalistic explanations. Thales and the transition to rational inquiry. Thales, though often associated with the flat Earth view, exemplified the Greek tradition of seeking explanations based on reason rather than myth. His contributions laid the groundwork for later thinkers like Pythagoras and Aristotle, who would eventually propose and prove the Earth's spherical shape. Philosophical context. Early Greek philosophy often sought to reconcile observable phenomena with abstract principles. The flat Earth hypothesis, while incorrect, was part of a broader effort to systematize human understanding of the cosmos, a precursor to scientific thought. Social and cultural implications. The persistence of flat Earth beliefs highlights the role of societal structures and cultural paradigms in shaping knowledge. Shared beliefs as societal glue. In ancient societies, shared cosmological beliefs served as a unifying force, aligning with religious rituals, agricultural practices, and governance. Questioning such beliefs would not only challenge scientific understanding but also the societal order. Lack of contradictory evidence. For the vast majority of people, daily experiences provided no reason to doubt the flat Earth hypothesis. Without long-distance travel or advanced astronomical tools, there were few opportunities to encounter evidence contradicting the flat Earth model. Endurance of mythology. Even as scientific theories began to emerge, mythological and religious frameworks continued to hold sway over the collective imagination, delaying the widespread acceptance of a spherical Earth. Significance of the flat Earth hypothesis in historical context. While the flat Earth hypothesis is now disproven, its historical significance lies in its demonstration of human reasoning within the constraints of available knowledge. A natural starting point. The hypothesis reflects a logical starting point for early civilizations grappling with the complexity of the universe. It shows the progression of thought from simple observation to complex reasoning. Foundation for future inquiry. The flaws in the flat Earth model prompted critical inquiry and debate, ultimately paving the way for discoveries that reshaped humanity's understanding of the cosmos. Cautionary tale. The persistence of the flat Earth hypothesis serves as a cautionary tale about the dangers of relying solely on surface-level observations without rigorous testing and evidence. The spherical Earth evidence emerges, the role of Greek philosophers. Pythagoras and the beginnings of a spherical Earth model. Pythagoras, 6th century BCE, was one of the earliest proponents of the spherical Earth. While his assertion may have stemmed from aesthetic or philosophical reasoning, such as the idea that spheres are the perfect shape in nature, it was an important shift from earlier flat Earth assumptions. Pythagoras' influence laid the groundwork for later philosophers to develop evidence-based arguments supporting the Earth's spherical shape. Aristotle and empirical evidence. Aristotle, 384 to 322 BCE, is perhaps the most significant figure in this transition, as he relied on empirical observations rather than purely theoretical ideas. His arguments for a spherical Earth were grounded in evidence, making them more compelling to his contemporaries and subsequent generations. Key observations supporting a spherical Earth. The shape of the shadow on the Moon. Lunar eclipses. During a lunar eclipse, the Earth passes between the Sun and the Moon, casting a shadow on the Moon's surface. Aristotle observed that this shadow is always circular, regardless of the Earth's orientation relative to the Sun and Moon. Implication: a flat disk Earth would cast an elongated or distorted shadow at certain angles, while only a spherical Earth can consistently produce a circular shadow. This was one of the earliest pieces of observational evidence supporting the Earth's shape. Strength of argument: this phenomenon was widely observable, and the consistent round shadow provided a straightforward and logical conclusion. The disappearance of ships over the horizon. Observation: as ships sail away, the hull disappears from view first, followed by the mast. Aristotle interpreted this as evidence of the Earth's curvature. If the Earth were flat, the entire ship would shrink uniformly as it moved farther away. Geometric implication: this observation demonstrates that the Earth's surface curves downward, obstructing the lower parts of an object first. It directly contradicts the flat Earth model, which would not allow such partial obstruction. Practicality of evidence: this observation was accessible to anyone near a body of water, making it a powerful, easily verifiable argument. The changing sky. Constellations and latitude. Aristotle noted that as travelers moved north or south, the visible constellations changed. For instance, moving northward revealed stars closer to the north celestial pole. Moving southward caused the North Star, Polaris, to dip closer to the horizon and eventually disappear below it. Spherical implication: this phenomenon can only occur on a curved surface. On a flat Earth, the entire sky would remain constant regardless of location. Connection to geometry: this observation ties directly to the concept of latitude and the geometry of spheres, marking an early understanding of the Earth's three-dimensional nature. Advancements in geometry and astronomy. The acceptance of the spherical Earth model was not solely based on observation. The integration of geometry and astronomy played a pivotal role. Eratosthenes' measurement of the Earth's circumference. Around 240 BC, Eratosthenes, a Greek mathematician and astronomer, used geometry to estimate the Earth's circumference with remarkable accuracy. He observed the angle of sunlight in two different cities, Alexandria and Syene, at the same time of day and calculated the Earth's size based on the difference in shadows. Significance: this experiment not only demonstrated the Earth's spherical shape but also quantified it, solidifying the model with mathematical precision. The role of geometry. Greek mathematicians like Euclid developed geometric principles that were later applied to astronomical phenomena. For instance, the concept of great circles, shortest paths between 2 points on a sphere, became fundamental in understanding navigation and the Earth's surface. The scientific method and the spherical Earth model. The transition from a flat Earth hypothesis to a spherical Earth model represents an early triumph of the scientific method. Empirical evidence over assumptions. The spherical Earth model emerged not as a philosophical idea but as a theory backed by observable and reproducible phenomena. Each piece of evidence, shadows during lunar eclipses, the behavior of ships over the horizon, and changing constellations, provided tangible, verifiable support. Integration across disciplines. The synthesis of observational astronomy, geometry, and early physics, such as understanding gravity's role in shaping celestial bodies, allowed the spherical Earth theory to gain widespread acceptance. Falsifiability and progress. Unlike the flat Earth model, which could not account for many observed phenomena, the spherical Earth theory made predictions that could be tested and confirmed, exemplifying the self-correcting nature of science. Social and cultural impact of the transition. Challenge to traditional beliefs. The shift to a spherical Earth model represented a move away from traditional, mythological worldviews toward evidence-based reasoning. This transition faced resistance but ultimately paved the way for the scientific revolution. Navigation and exploration. Acceptance of a spherical Earth was crucial for advancements in navigation and exploration. For example, understanding the Earth's curvature allowed sailors to predict routes and distances more accurately, ultimately enabling voyages like Christopher Columbus's journey to the Americas. Education and dissemination. Greek philosophers' works were later preserved and expanded upon by Islamic scholars and European Renaissance thinkers, ensuring the spherical Earth model became a cornerstone of scientific education. Significance of these observations today. A model for scientific reasoning. The evidence supporting the spherical Earth remains a textbook example of how empirical observation and logical reasoning can overturn long-held assumptions. Combating modern misinformation. In an age where flat Earth theories have seen a resurgence in certain circles, revisiting these classical arguments reminds us of the enduring power of evidence-based thinking. Inspiration for curiosity. The journey from flat Earth to spherical Earth theories exemplifies humanity's drive to understand the unknown. It inspires continued curiosity and exploration in the pursuit of truth. Flat Earth in the Middle Ages, the persistence of flat Earth beliefs. Communities holding on to the flat Earth hypothesis. During the Middle Ages, scientific progress slowed in certain parts of the world due to a combination of factors, including political instability and the dominance of religious dogma. This allowed the flat Earth hypothesis to persist in some communities. Flat Earth beliefs were more common among the general population, who lacked access to formal education. Folklore, mythological traditions, and religious interpretations often reinforced these views. Why did flat Earth ideas persist? Limited access to knowledge, literacy rates were low during the Middle Ages, and scientific knowledge was concentrated in monasteries and among scholars. For most people, the idea of a flat Earth remained unchallenged because they had no exposure to the evidence supporting a spherical Earth. Reliance on visual perception, the horizon still appeared flat to most observers, and without empirical tools or education, the flat Earth view seemed logical. Cultural inertia, long-standing myths and traditions take time to fade, especially when they are intertwined with religious or societal beliefs. Scientific progress in the Middle Ages. Contrary to the misconception that the Middle Ages were entirely regressive, this era saw significant advancements in science and philosophy, particularly among educated Europeans. Scholarly acceptance of the spherical Earth. Thomas Aquinas, a leading theologian and philosopher of the 13th century, incorporated the spherical Earth into his synthesis of Christian theology and Aristotelian philosophy. His work demonstrated that the spherical Earth was compatible with religious doctrine, bridging the gap between science and faith. Dante Alighieri, in the Divine Comedy, Dante described a cosmology based on a spherical Earth, complete with a southern hemisphere and the concept of gravity directing all things toward the Earth's center. His poetic depiction reflected the mainstream understanding of his time. These examples highlight that among educated scholars, the spherical Earth model was widely accepted and integrated into intellectual thought. Sources of knowledge. European scholars in the Middle Ages relied heavily on the works of ancient Greek and Roman philosophers, as well as Islamic scholars, who preserved and expanded upon classical knowledge. The writings of figures like Ptolemy and Aristotle, which supported a spherical Earth, were widely studied and respected. The Enlightenment myth: everyone believed in a flat Earth. The notion that the Middle Ages were dominated by flat Earth beliefs is a misconception propagated during the Enlightenment. Here's why this myth emerged and gained traction. Enlightenment narrative. Enlightenment thinkers sought to distinguish their era from the perceived ignorance of the medieval period. By portraying the Middle Ages as intellectually backward, they reinforced the idea of progress and reason as hallmarks of the Enlightenment. The flat Earth myth was an easy way to depict the Middle Ages as a dark time in contrast to the light of Enlightenment rationality. Washington Irving's influence. In the 19th century, Washington Irving's biography of Christopher Columbus further popularized the idea that medieval people believed in a flat Earth. Irving dramatized Columbus's struggle as convincing a flat Earth-believing clergy to let him sail west, which was historically inaccurate. This romanticized account perpetuated the falsehood and cemented the flat Earth myth in popular culture. Role of the Church and religious institutions. Support for the spherical Earth model. Contrary to the stereotype of the Church opposing science, many medieval scholars, including clergy, supported the spherical Earth model. For instance, the Venerable Bede, 8th century, wrote about the Earth's roundness in his astronomical works. Monasteries served as centers of learning, preserving classical texts that supported a spherical Earth. Integration with religious cosmology. The Church often framed the spherical Earth model within a religious cosmology. This integration helped reconcile scientific evidence with theological beliefs, reducing resistance to the spherical Earth model among educated religious figures. The Middle Ages, a time of transition. While the Middle Ages were not the scientific zenith of human history, they were far from an age of ignorance. The persistence of flat Earth beliefs among the general population coexisted with a growing body of scholarly work that supported the spherical Earth. This duality reflects the complexity of intellectual development during this era. Education and knowledge transmission. The rise of universities in the later Middle Ages, such as those in Bologna and Paris, facilitated the spread of knowledge about the spherical Earth. By the 12th century, translations of works by Islamic scholars like Al-Farabi and al-Biruni, who supported a spherical Earth, further enriched European scholarship. Setting the stage for the Renaissance. The medieval preservation of classical knowledge laid the groundwork for the scientific revolution during the Renaissance. The spherical Earth model, once debated, became an uncontested truth in the scientific community. Modern lessons from medieval flat Earth beliefs. The persistence of flat Earth ideas during the Middle Ages serves as a case study in the dynamics of knowledge and belief. Cultural and educational gaps. The divide between educated elites and the general population highlights how knowledge dissemination is crucial for combating misinformation. Endurance of myths. The flat Earth myth about the Middle Ages reminds us of the power of narratives, even those that lack historical accuracy, to shape public perception. The role of education. Just as medieval scholars preserved and advanced knowledge within their constraints, modern education systems play a critical role in promoting scientific literacy and critical thinking. The Flat Earth Revival in Modern Times. This section examines the surprising resurgence of flat Earth beliefs in the 21st century, despite overwhelming scientific evidence against the hypothesis. The persistence and growth of these ideas shed light on broader societal trends, psychological mechanisms, and the impact of technology. The resurgence of the flat Earth hypothesis. Historical context of revival. The flat Earth hypothesis, largely dormant for centuries, began to resurface in the mid-20th century with groups like the Flat Earth Society. While initially small and fringe, these ideas gained traction with the advent of the internet and later social media, which provided a platform for dissemination and community building. The movement reflects a broader phenomenon where pseudoscientific ideas gain visibility and credibility in the absence of rigorous scrutiny. Why it matters in the 21st century. The revival of flat Earth beliefs challenges the assumption that scientific literacy and technological progress naturally eliminate outdated or disproven ideas. Understanding why these beliefs persist provides insight into the dynamics of misinformation and the psychology of conspiracy theories. Key factors driving the modern revival. 1. Distrust in authority. Deep-rooted skepticism. Many flat Earth proponents express a profound distrust of authoritative institutions, such as governments, space agencies, e.g., NASA, and the scientific community. This skepticism often extends to evidence that contradicts their beliefs, such as satellite images or space exploration missions, which are dismissed as fabrications or part of a global conspiracy. Origins of distrust. Historical events like the Cold War, misinformation campaigns, and real-world scandals, e.g., Watergate, have eroded public trust in institutions. Flat Earth believers often view themselves as part of a countercultural movement that resists perceived manipulation by powerful elites. Psychological dynamics. Distrust in authority is often rooted in cognitive biases such as the illusion of explanatory depth, where individuals believe they understand complex systems, like the Earth's shape, better than they actually do. Believers find comfort in rejecting official narratives, which they perceive as tools of control. 2. Echo chambers and social media. Role of social media. Platforms like YouTube, Facebook, and Twitter have played a pivotal role in the Flat Earth revival. Algorithms designed to maximize engagement often promote sensational or controversial content, giving Flat Earth theories disproportionate visibility. Social media fosters echo chambers, where users are exposed primarily to content that reinforces their existing beliefs. Confirmation bias. Flat Earth communities thrive on confirmation bias, the tendency to seek out and prioritize information that supports pre-existing views while ignoring contradictory evidence. For instance, Flat Earth videos on YouTube often link to similar content, creating a feedback loop that amplifies belief in the hypothesis. Community dynamics. Social media also provides a sense of belonging for Flat Earth proponents. Being part of a group that shares their views creates a supportive environment, making it easier to dismiss dissenting opinions. 3. Appeal to common sense. Simplistic observations. Flat Earth arguments often rely on observations that appear intuitive. The horizon looks flat, so the Earth must be flat. We cannot feel the Earth spinning, so it must be stationary. These claims exploit the human tendency to trust sensory experiences over abstract or complex scientific explanations. Cognitive misconceptions. The reliance on common sense often reflects cognitive biases, such as the availability heuristic, the tendency to overestimate the validity of information that is easily recalled. Flat Earth proponents use common sense as a rhetorical tool to frame their arguments as accessible and logical, even when they conflict with scientific evidence. Mistrust of complexity. Many Flat Earth believers find comfort in rejecting the complexities of modern science, which can seem inaccessible or alienating. Flat Earth theories offer a simpler, more relatable worldview. The broader implications of Flat Earth beliefs. Misinformation in the digital age. The Flat Earth movement highlights the broader challenge of combating misinformation online. Social media platforms often prioritize engagement over accuracy, allowing pseudoscientific ideas to spread unchecked. The movement exemplifies the dangers of unchecked virality, where sensational content can overshadow evidence-based discourse. Conspiracy culture. Flat Earth beliefs often overlap with other conspiracy theories, such as the denial of the moon landing, anti-vaccine movements, or climate change denial. This interconnected web of conspiracies reflects a growing culture of skepticism toward mainstream narratives, driven by a mix of political, psychological, and social factors. Erosion of scientific literacy. The resurgence of Flat Earth ideas underscores gaps in public understanding of basic scientific principles. Addressing this requires renewed investment in science education and public outreach. The role of identity and belonging. For many believers, the Flat Earth hypothesis is less about evidence and more about identity. Being part of a community that rejects mainstream science provides a sense of purpose and defiance, making it difficult to change their minds through rational argument alone. Modern scientific counterarguments. Observable evidence. Photographs from space consistently show the Earth as a sphere. These images are corroborated by independent space agencies worldwide. Airplane navigation and GPS systems rely on a spherical Earth model, which accurately predicts distances and flight paths. Physical phenomena. Gravity naturally forms large celestial bodies into spheres, as this shape minimizes potential energy. Time zones and the Coriolis effect, which influences weather patterns, are only explainable on a rotating, spherical Earth. Scientific transparency. Space exploration is conducted by multiple organizations across different nations. The sheer scale of coordination required for a global conspiracy would be implausible. Lessons from the Flat Earth Revival. Understanding belief systems. The Flat Earth movement is a reminder that beliefs are shaped not only by evidence but also by social, emotional, and psychological factors. Addressing these beliefs requires empathy and engagement rather than ridicule, as mockery often reinforces opposition. The power of education. Promoting critical thinking and scientific literacy is essential to countering misinformation. Education systems must emphasize not just facts but also the process of scientific inquiry and evidence evaluation. The role of technology. Social media platforms must take responsibility for curbing the spread of misinformation. Improved algorithms, fact-checking, and content moderation can help reduce the visibility of pseudoscientific ideas. Debunking flat Earth claims. 1. Gravity explains it all. Scientific basis. Gravity is a fundamental force responsible for the formation of celestial bodies into spheres. When matter accumulates, gravitational forces pull it inward evenly from all directions, resulting in a spherical shape. This principle applies to planets, moons, and stars. A flat Earth would contradict this natural tendency. Without consistent gravitational forces across its surface, a flat Earth would collapse into a more stable, spherical shape. Flat Earth counterarguments. Some flat Earth proponents claim that gravity does not exist and suggest alternative explanations, such as density and buoyancy. However, these concepts fail to account for why objects fall toward the Earth's surface or why celestial bodies form spheres. Logical refutation. The spherical shape of Earth is not just a result of theoretical physics but is observable in countless celestial objects. The universality of this phenomenon strongly supports the spherical Earth model. 2. Airplane navigation. Practical evidence. Long-distance flights utilize great circle routes, which are the shortest paths between 2 points on a sphere. These routes appear as arcs on a two-dimensional map but are direct and efficient when accounting for Earth's curvature. Flat Earth models cannot explain the necessity of these routes or the consistent success of global navigation systems like GPS, which depend on a spherical Earth for accuracy. Flat Earth counterarguments. Proponents often claim that flight patterns are manipulated or that pilots are part of a conspiracy. However, such claims lack credible evidence and would require an implausibly vast network of collusion among airlines and aviation authorities. Logical refutation. The global aviation industry operates transparently, with millions of flights adhering to scientifically validated principles of navigation. The precision and consistency of these systems are incompatible with flat Earth models. 3. Photos from space. Empirical evidence. Satellite imagery and photographs taken by astronauts consistently show Earth as a sphere. These visuals are corroborated by independent space agencies worldwide, including NASA, ESA, and JAXA. Flat Earth counterarguments. Many flat Earth proponents dismiss these images as fabrications, claiming that space exploration is part of a conspiracy. They suggest that images are digitally created or manipulated. Logical refutation. The sheer volume of imagery, spanning decades and originating from multiple independent organizations, makes the conspiracy argument untenable. Additionally, amateur astronomers with telescopes can observe planetary bodies, further validating spherical models. 4. Time zones. Observable reality. Time zones exist because Earth is a rotating sphere. As the planet spins, different regions experience sunlight at different times, creating day and night cycles. A flat Earth would struggle to account for the continuous progression of time zones, especially phenomena like polar day and night, where the sun does not set or rise for months. Flat Earth counterarguments. Some flat Earth models suggest alternative mechanisms for sunlight distribution, such as a local sun circling above a flat plane. However, these models fail to replicate observed phenomena, such as the length of shadows and the sun's varying angles across latitudes. Logical refutation. The consistency of time zones, along with global synchronization of events like international communication and travel, is explainable only on a spherical Earth. Flat Earth models cannot accommodate these realities without introducing contradictions. Why does this debate matter? The Flat Earth debate extends beyond the specifics of Earth's shape. Its persistence has broader implications for society, scientific literacy, and the fight against misinformation. 1. Scientific literacy. Challenge to critical thinking. Flat Earth beliefs reflect a rejection of evidence-based reasoning and scientific principles. Allowing these ideas to flourish undermines public understanding of science and the methods used to arrive at objective truths. Broader impact. If society tolerates the rejection of basic scientific facts, it sets a precedent for dismissing other critical issues, such as climate change, vaccination, and public health policies. Combating flat Earth beliefs is therefore part of a larger effort to promote scientific literacy and rational discourse. 2. The power of conspiracy theories. Mechanisms of spread. The Flat Earth movement illustrates how conspiracy theories gain traction through distrust of authority, social media echo chambers, and cognitive biases. It serves as a case study in how misinformation thrives in the digital age, where algorithms amplify controversial content and foster communities that resist correction. Broader relevance. Understanding the flat Earth phenomenon can help society address other forms of misinformation, from anti-vaccine movements to political disinformation campaigns. It highlights the need for strategies to counteract misinformation while respecting freedom of speech. 3. The role of education. Filling knowledge gaps. The Flat Earth movement exposes gaps in education systems, particularly in teaching critical thinking and scientific inquiry. Addressing these gaps is essential to equip future generations with the tools to evaluate evidence and resist misinformation. Encouraging curiosity. While debunking flat Earth claims is important, fostering curiosity and a genuine understanding of science is even more impactful. Providing accessible explanations and engaging educational resources can help counter the allure of pseudoscience. Modern implications and lessons. Addressing misinformation. The Flat Earth movement underscores the importance of proactive measures against misinformation. Public outreach campaigns, fact-checking initiatives, and responsible use of technology can help curb the spread of pseudoscience. Fostering dialogue. Ridiculing flat Earth believers often reinforces their opposition. Instead, engaging in respectful dialogue and addressing their concerns with evidence can create opportunities for education and understanding. Preserving trust in science. Rebuilding trust in scientific institutions and emphasizing transparency are essential. Public communication should not only share conclusions but also explain the processes and evidence that lead to them. So is the Earth flat?